Hello everyone, this is my 12th lecture, and in this lecture we shall discuss about the torque on a dipole in uniform electric field. Yesterday we have discussed about the electric field intensity due to dipole in the two cases, number 1 on axial line and number 2 on equatorial line. And today we shall discuss about the torque on a dipole in uniform electric field. For the case we consider or we draw electric line of forces for uniform electric field, and we have earlier discussed in electrolytic line of forces that for uniform electric field the electric line of forces are parallel to one another, because in uniform electric field the electric field intensity is equal at all points, so the separation of electric line of forces never changes in uniform electric field. So the electric line of forces for uniform electric field are parallel to one another. This is a dipole and this is minus Q charge and this is plus Q charge. This point is A and this point is B. Because electric line of forces moves from positive to negative, so this negative charge will experience an electrostatic force will be QE opposite to the direction of electric field, and this positive charge will experience a force QE, because in uniform electric dipole the charges are equal, electric field intensity is equal at this point, so QE both are equal. These two forces QE and QE are equal in magnitude and opposite in direction. So the total force on the dipole in uniform electric field is 0. But the line of forces for both the forces are separate, so that produces a torque, and which we shall discuss in our topic. So in order to calculate the torque, we increase this line of forces. We draw a perpendicular on it. If the angle of dipole with electric field is theta, and this is the separation of charges is 2a, then the torque will be either force into perpendicular distance. Now consider a dipole of charge plus minus Q, separation of charges 2a, and midpoint O. This is the midpoint. This point is, it is placed in uniform electric field of intensity I. Uniform electric field intensity A. So, total force on dipole QE plus minus QE is equal to 0. FA plus FB, both forces are equal in magnitude and opposite in direction, so the total force on dipole will be 0. But since line of forces are different, so they produces, but since line of forces are different, so they produces a torque. And according to the definition of the torque, torque is equal to either force into perpendicular distance between the forces, perpendicular distance, to is the symbol, either force is QE and perpendicular distance is BC. This is equation number first. In triangle ABC, BC upon AB, perpendicular upon perpendicular upon hypotenuse is equal to sine theta. So BC is equal to AB sine theta. And value of AB is the separation of charges to A sine theta, this distance. So torque will be is equal to tau is equal to QE into 2A sine theta. Or tau is equal to Q into 2A into E sine theta. Or tau is equal to PE sine theta. In vector notation, tau is equal to P cross E. This is the cross product of electric dipole moment and electric field intensity. There are two special cases. If we consider sin theta and cos theta in formula, then tau is equal to Pe sin theta. The first case, if theta is equal to 0, means dipole is parallel to electric field, or theta is equal to 180, means anti-parallel. Parallel means electric line of forces are these, and dipole is this, minus q plus. This is parallel, means theta is equal to 0, and for anti-parallel, these are the electric line of forces, and dipole will be along this. This is minus q and this is plus. For theta is equal to 180. And we know that sin 0 is equal to 0, sin 180 or sin pi is equal to also 0, so torque will be 0. If dipole is parallel or anti-parallel, then it will not experiences any torque in electric field. And for the second case, if theta is equal to 90, then sin 90 is equal to 1. Electric line of forces are these, and dipole is in this type, minus q to plus. In this case, the dipole is perpendicular to the electric field, and theta is equal to 90 is equal to sin 90 is equal to 1. So torque is equal to P E sin 90. The maximum value, so torque will be maximum and it will be equal to P. Energy of dipole in uniform electric field for today's lecture, and sometime it is discussed in the next chapter, but we shall discuss this derivation in this chapter. So again we consider a uniform electric field. This is a uniform electric field and the position of dipole is this, minus q plus q, this angle is theta 1. Now the dipole is rotated in the electric field, no doubt about that. This charge and this charge, both charges experiences a force, and then when this dipole is rotated, we have to do a certain work against the torque. This angle is theta 2. So we have to do a certain work in the rotation of dipole against torque, this work done is stored in the dipole in the form of potential energy called energy of dipole in uniform electric field. So work done in rotating the dipole, in uniform electric field against the torque is stored in the dipole in the form of potential energy called electrostatic potential energy of dipole. This is the definition of energy of dipole. When a dipole is rotated, a work is done against the torque, and this work done is stored in the dipole in the form of potential energy. So in order to calculate the work done, W is equal to, we know that, integral to d theta, and theta 1 to theta 2. And we know that in earlier derivation, tau is equal to Pe sin theta. So W is equal to integral theta 1 to theta 2 Pe sin theta d theta. Pe is a constant quantity, dipole moment of an electric field. Sin theta d theta, theta 1 to theta 2. So value of integration of sin theta will be is equal to minus cos theta, theta 1 to theta 2. We put above limit first, minus sign can be taken out, cos theta 2 minus cos theta 1. Again we take negative sign inside the bracket, so W is equal to Pe cos theta 1 minus cos theta 2. This is the work done in rotating the dipole from theta 1 to theta 2 in uniform electric field of intensity E, if theta 1 is equal to 90 degree, theta 2 is equal to theta. So W is equal to minus Pe cos theta. This is theta and this cos 90 is equal to 0. So W is equal to minus Pe cos theta, and this is the potential energy of dipole in uniform electric field. W is equal to U is equal to minus W is equal to Pe cos theta. So this is the potential energy or electric potential energy of dipole in uniform electric field intensity. Now we shall again discuss about the special cases, and we have discussed that if theta is equal to 0, then cos 0 is equal to 1, then UE is equal to minus PE. UE is equal to minus PE. This is the minimum potential energy of the dipole. Minimum potential energy of dipole We can also consider minus P cos theta. So UE is equal to minus PE if theta is equal to 180. Then cos 180 is equal to minus 1 and UE is equal to this minus. Okay. So UE is equal to minus PE and cos 180 is minus 1, so plus PE. So potential energy will be mixed. And because we know that in these cases theta is equal to 0 also, and in this case theta is equal to 0, torque is equal to 0 and torque is equal to 0, means in this case the torque is not experienced by the dipole and potential energy is minimum. So this state is called stable equilibrium state. Stable equilibrium state. Theta is equal to 0 is called stable equilibrium state. In this case also the torque is 0 but the potential energy is maximum. This is called unstable equilibrium state. Means theta is equal to 180 is unstable equilibrium state, and theta is equal to 0. Stable equilibrium state of dipole is this, and then this is the torque, and if theta is equal to 90, then cos 90 is equal to 0, then dipole potential energy will be equal to 0 in this case. So theta is equal to 0, stable equilibrium, theta is equal to 180, unstable equilibrium state. This is the derivation. Again I am repeating, W is equal to theta 1 to theta 2 d theta. We put the value, P is sin theta d theta, PE can be taken out, sin theta d theta. The integration of sin theta is minus cos theta. We put the upper limit, minus can be taken out, cos theta 2 minus sin cos theta 1. Again negative sign is taken inside the bracket, then value will be VPE cos theta 1 minus cos theta 2. If theta 1 is equal to 90, theta 2 is equal to theta, then W is equal to minus P cos theta. So this further will be stored in the dipole in the form of potential energy. So minus PE cos theta, and if theta is equal to 0, then cos 0 is equal to 1. So with negative minimum potential energy, this is called stable equilibrium state. Theta is equal to 180, cos 180 is equal to minus 1. So plus PE, stable or unstable equilibrium state. If we change the position of dipole with this state, then the dipole returns to this state. That's why this is called stable equilibrium state. And at theta is equal to 180, if we change the position of dipole, then it never returns to the theta is equal to 180. So this is called unstable equilibrium state.